Okay, so welcome to this next video in the playlist on functional analysis. In this video what we're going to do is use what we've studied in the previous video about how the CAB metric space, so the set CAB, which is the set of all continuous functions on the interval AB, with the Supremum metric on it, what we've seen is that that is a complete metric space, and basically we're going to do an example of how we can use that information constructively. It's a complete metric space. Okay, right, so we're going to start off with a sequence of functions from this set, which is going to be a Cauchy sequence of functions, and we're going to show that it's Cauchy with respect to this d-infinity metric, and then what we're going to do is use the fact that it's a complete metric space to say that, okay, if this is a Cauchy sequence of functions, it therefore must have a limit, and then what we'll use is the fact that if it's got a limit in this metric space, then the limit is the function which this sequence of functions converges to pointwise. So then we'll take the pointwise limit and bingo, we have our limit in this metric space. So the sequence of functions we're going to look at is firstly, actually I need to firstly tell you what interval we're going to be looking at. So we're going to be looking at the interval 0 to a half. So our a is equal to 0 and our b is equal to a half, basically. And the sequence of functions s is going to be the sequence 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed, etc. So if I want to tell you what the nth term of this sequence is, Sn, where n can vary from 1, 2, 3, 4, etc., it's going to be the sum from r is equal to 1 well, what we're going to need, because we want this to be the first term, so we'll need n plus 1, and then we'll put in x to the power of r, basically. In fact, okay, that actually needs to be from r is equal to 0 to n, potentially. Is that correct? We're going to have some difficulty with this getting here. Actually, yes, we'll keep it from r is equal to 1 to n plus 1 and just subtract 1 off there. Is that correct now? I think that is. So the first term here, S1, is just going to be the sum from r is equal to 1 to 1 plus 1, which is 2. And then you'll get r is equal to 1, you'll put in there. No, this isn't right. So we need to alter this somehow to make it correct. I think if we just take that down to n, then it might work. Okay, so if S1, if we plug in n is equal to 1 up here, we'll get the sum from r is equal to 1 of x to the power of r minus 1. Now we plug in 1, and we get x to the power of 0, so that just becomes 1. And then if we ask what is S2, again, it will go from the sum from r is equal to 1 to 2 this time of x to the r minus 1. That's better. So then we've got 1 for the first one, and then when we plug in r is equal to 2, we'll get plus x. So basically it's a series. And we know that this, what we know is that this is a very familiar series, basically. As the n gets bigger and bigger and bigger, you're going to add more and more terms in, and it's going to basically be a geometric series. However, this is now a function. We're viewing this as being a function of x, where x is an element of the interval 0 to a half, basically. Okay, so we want to prove that this sequence is Cauchy, basically, and to prove that it's Cauchy, what we need to prove is that for any epsilon, for all epsilon greater than 0, there exists some big N, which is an element of the natural numbers. So there exists some point in this sequence such that if you take any 2 points, little n and little m, which are greater than or equal to big N, then the distance in this metric space, d infinity, of the function f little n evaluated of x, and the function f little m of x, that distance is going to be less than epsilon. Okay, so we need to find a little n, we need to find a big N for a given epsilon. So we need to say, okay, we have some epsilon, can we find a big N such that this condition is satisfied? Now what is the this distance infinity function in this metric space? Well, that is just going to be the supremum over x is an element of the interval 0 to a half of the modulus of fn minus fmx. And now if we just substitute in what those functions are, basically. So the nth function in here goes up, unfortunately, to the n minus 1 power. So for instance, this is the first term here. It might have been more sensible just to relabel this the 0th term, this is the first term, but we've done it the other way around. So we label this the first term, second term, third term, but you'll notice that this first term is a polynomial of degree 0, this second term is a polynomial of degree 1. So basically it goes up to the degree term that's 1 minus the term that it is in the sequence, basically. So the third term goes to degree 2, the fourth term goes to degree 3, etc. Okay, so if we put in what these two functions are, then basically what we are taking the supremum of over x is an element of the interval, and let me move this up, over x is an element of the interval 0 to a half, is the modulus of this fn function, which is 1 plus x squared plus all the way up to x to the n minus 1 minus 1 plus x squared all the way up to x to the n minus 1. Okay, and if we take the difference between those two, if we assume temporarily that n is greater than little n, then when we take the difference of those two, this one is going to go to a higher degree than this one here. So you're going to get a few terms left over, the terms that were on this nth function that weren't on this nth function. Okay, so we'll get, we can do that without loss of generality, because if the nth one is bigger than the nth one, all you're going to get is this one will have terms that this one doesn't. So it'll go up past little n minus 1, and you'll have x minus 1, n minus 1 is great, you know, is a degree beyond this. And when you subtract that off, you're going to get negative terms, and then you're just taking the modulus of that n away, so it doesn't matter, basically. So without loss of generality, we'll just say that n is beyond n. If you want an easier argument for why that is, then if m is greater than n, just multiply this inside basically by minus 1, get fm in the front and fn being the one that you're subtracting off. The modulus sign means that you can do that because it doesn't actually affect the value that you get. Okay, so this is the supremum, the supremum of x is an element of the interval 0 to a half of the modulus of what we end up with is you're going to subtract off the x to the n minus 1 terms. You're going to end up with x to the n plus x to the n plus 1 all the way up to x to the n minus 1. So basically we assumed that n was greater than little n. So this polynomial here, this fnx, went much beyond this polynomial fm of x. So back here somewhere, let's say, was the term xm minus 1 of x, and it went on, this polynomial went on up to xm plus xm plus 1, etc. And when we subtracted all of these off, all of these cancel with all of these here, and all you're left up with is this xm plus 1 all the way up to the plus x to the n minus 1. Okay, right. Now if you want to take the supremum over x as an element of this interval 0 to a half, then where is this polynomial going to be maximum, basically? Where is this difference between the two polynomials fn of x and fm of x going to be a maximum? Well, it's going to be when you evaluate it at a half. Okay, so I hope that's pretty obvious, because all of these terms here, these x to the power of some integer, they're going to get bigger as you make the number bigger, and they're going to get smaller as you make the number smaller. So the way you can maximize this sum of these polynomial terms is by evaluating it at the biggest possible number, and the biggest possible number we're allowed to evaluate it at is a half. So the supremum over x as an element of 0 to a half is in fact going to be this polynomial evaluated at a half. We can also drop the modulus signs because this is going to be a positive value. Always, for whatever number you stick in between 0 and a half, this is going to be a positive value. Okay, so what we get is a half to the power of m plus a half to the power of m plus 1 plus all the way up to a half to the power of n minus 1. Okay, so it's a portion of geometric series, basically, but a finite one in this case, so a geometric sum, if you like. So if we want to work out what this is, then basically we can pull out a half to the power of m, so let's do that. So we pull out the half to the power of m, then we end up with 1 plus a half plus, and you go on all the way up to a half to the power of n minus 1 minus m, basically. And we know that m minus 1 is greater than m. We certainly assumed that m was going to be greater than m. And if n is greater than m, then n is at least 1 greater than m. So when you subtract off m from n, then you're going to end up with at least 1, so you're going to get some positive number in this. Okay, right. So this thing here, this 1 plus a half plus whatever it is going to be less than the sum. This thing here, so let me get the highlighter. This thing that you have here is going to be less than, strictly less than, the sum from r is equal to 0 to infinity of a half to the power of r, i.e. this is the infinite sum. So this is 1 plus a half, so that's 1 is when you evaluate this at 0, so r is equal to 0, you get 1. What r is equal to 1, you get a half. Then r is equal to 2, you get a half to the power of 2, etc., and it goes on. So this is a finite portion of this infinite series, basically, and we know what this evaluates out at. This evaluates out to be 2, basically, this infinite series, and let me just give an argument for why that is. So if you've got this infinite series, 1 plus a half squared, plus a half cubed, etc., and you want to know what does that converge on, then let's call the value that it converges on s. And yes, it's sloppy, but we'll say that s is equal to this infinite sum. Okay. Right. Then what you can do is multiply s by a half, and what you'll get is a half plus a quarter, which is a half squared, plus this one multiplied by a half, you'll get a half to the power of 3. Plus this one evaluated at a half, you'll get half to the power of 4, etc. Okay, and if you then subtract half s away from s, so if you take s minus a half s, then what you're going to get, this term will cancel with this term will cancel with this term, so let me get the highlighters. This term here will cancel with this term here, this term here will cancel with this term here, this term here will cancel with this term here, etc. And that will go on forever and ever and ever and ever. So this basically will end up equaling just the one term that was left over, which is this 1. And then if we factor out the half, we'll get if we factor out the s, we'll get s times 1 minus a half, which gives us a half, is equal to 1. So we get that a half s is equal to 1, therefore s is equal to 2. That's a nice intuitive argument for why this infinite sum is equal to 2. Okay, you can of course prove it from a axiomatic limit point of view. So this whole thing here, is going to be strictly less than. So this thing here, this difference basically, and remember how we got all of this mess? We got it all from asking what was the distance between the function fn of x and fm of x. And what we've now found is that the distance between any f little n and f little n is going to be strictly less than a half to the power of m times 2. So, if you want to, and where m was the lower of the two, basically, remember we assumed that the little m we'd chosen, was greater than the little m we'd chosen. So basically what we've shown is that the distance between this function f little m and this distance between the function f little m is going to be strictly less. So this here, never mind it being strictly less than epsilon, that's what we're trying to show. What we know is that this is going to be strictly less than 2 to the times a half to the power of m. Okay, so if you make little n and little m greater, so pick some little m, if you pick any little n which is greater than that little greater than that little m, then the distance between them is going to be strictly less than 2 times a half to the power of m. So if you now say, okay, if you've given me an epsilon, so my task, remember, was you give me an epsilon, I want you to be able to find me a big N such that if little n and little m are greater than or equal to big N, then the distance between those two functions is going to be less than epsilon. So my claim is, okay, set big N such that you give me this epsilon, I'm going to choose big N so that epsilon is equal to 2 times a half to the power of big N. And my claim is that if little n and little m are bigger than this big N, then this will be true. So firstly, let me get you an explicit formula for what big N is. So divide both sides by half, by 2 rather, multiply by half strictly, and then take well, you can either view this as being, the best way to view this is, okay, so let's do one step at a time, and I need some more paper. Let's get another piece of paper here. Okay, right, so what we had so far was we had that we were going to, you give me an epsilon. The way I was going to choose this big N was by using this equation, that 2 times a half to the power of big N should equal epsilon. So we then said that a half to the power of big N should equal epsilon over 2, and we've then got that 1 over 2 to the power of big N is equal to epsilon over 2, which gives us that 2 to the power of big N should be equal to 2 over epsilon. Okay, and then, I've made a slight mistake, in fact. I want epsilon to be greater, strictly greater. I might not be able to find equality, because remember, I've also got this condition that big N needs to be a natural number. You can find equality, of course, but you will have to accept that big N might need to be a real number, and we don't want that, so we'll make it an inequality that we need to obey instead. So I do apologise for that, so just replace these with inequality signs here. Okay, so now what we've done is we've taken both to the opposite sides, basically. So that was all fine because we were always multiplying by strictly positive numbers. So we never multiplied by a negative number. I multiplied basically on this side by 2 to the power of n and multiplied on this side by 2 to the power of n. That's assuredly a positive number. And then I multiplied by 2 on both sides and multiplied by 1 over epsilon, which is again a strictly positive number. So what we get is that 2 to the power of big N needs to be strictly greater than 2 over epsilon, and that gives us that big N needs to be strictly greater than log to base 2 of 2 over epsilon. So basically my claim is if you pick your big N such that it obeys this inequality here, then if you pick a little n and a little m which are greater than or equal to big N, then the distance in this metric space, in this supremum metric between the function f little n of x and f little m of x is going to be less than epsilon. That's my claim. Let me now prove that to you. Right, so if I've chosen my little n and my little m such that they are greater than or equal to big N, then the worst possible scenario is that little m is equal to this big N, basically. Remember, one of them is going to be lower than the other. Okay, so without loss of generality, let's say it's this little m. Now, the worst possible scenario is that little m is actually equal to big N, but in all other cases, it's going to be greater than or equal to big N. Now, we've shown that the distance function between f little n of x and f little m of x is strictly less than 2 to the power of a half, 2 times a half to the power of little m. So we showed that here, okay? So, I'm sorry, I don't think it actually ever focused. We showed that here. We showed that this distance function between f little n of x and f little m of x, if little m was less than little n, was going to be strictly less than 2 times a half to the power of little m. Okay? So, if little m is greater than or equal to big N, then it implies that 2 to the power of a half big N is strictly greater than 2 to the power of a half little m, because little m is greater than or equal to big N. So that implies that you are multiplying by a half in this one more times. So you're going to get something that's going to end up being smaller than this one because you're going to be multiplying by half by more times, and a half makes you smaller. If you multiply by half, it halves your size. Okay, this is going to be strictly less than, in fact it's going to be less than or equal to, again, because little m could equal little n. So this is going to be less than or equal to 2 to the power of a half big N. But we chose our epsilon, so that we chose our big N, so that epsilon was going to be greater than 2 to the power of a half to the big N. So what we can also say is that this is strictly less than epsilon, and therefore that implies that the distance between f little n of x and f little m of x is strictly less than epsilon. So basically what I've done is I've said, you give me an epsilon, I will construct you a big N from here, and I guarantee you that if you pick any two functions from the sequence of functions, f little n of x and f little m of x, which are beyond this term f big N of x in this sequence of functions, then that's going to be less than epsilon. So what I have done is I've shown you that this sequence S, which is 1 plus x, 1 plus x plus x squared, 1 plus x squared plus x cubed, etc. I've shown you that that is a Cauchy sequence of functions in this metric space CAB with the supremum metric on it. Okay, which, because this metric space is a complete metric space, therefore must have a limit within this metric space. And in the next video, what we're going to do is show how we can use the fact that it must convert. In fact, actually, we haven't got that much further to go, so we'll do it in this video. So now what we say is, okay, it does have a limit. What we then know is if it has a limit in here, its limit is its pointwise limit. Okay, but we know what this converges to pointwise. If we consider x now to be a fixed value, then what does this sequence converge onto? X is a fixed value in the interval 0 to a half. So what does this sequence converge onto? Well, it's a geometric series. So what does the sum from r is equal to 0 to infinity of x to the r, what does that converge on? Well, it's going to be the sum from 1 plus x squared, which is when r is equal to 2, plus x cubed when r is equal to 3, plus x to the 4, etc. Okay, so again what we can say is, okay, let's say this is our sum S. So this is a very nice argument for how you can easily remember what this converges to. You can then multiply S by this value x, which we are viewing just as a constant because we're asking what does this converge to pointwise. And remember, when we take the pointwise limit, what we do is we say, okay, fix the value in this interval on which the function is defined, plug in that value into the functions, and then take that sequence of resulting real numbers and ask what does it converge to in the metric space of the real line. If we multiply x, this sequence S by x, so that's what we're doing now. We've taken this sequence, we're evaluating x, we're imagining that x now represents a specific point in this interval 0 to a half, so it's just a constant as far as we're concerned. So we're multiplying this sequence by x, and we get x plus x squared plus x cubed, etc. Okay, and then we say, okay, what happens if we take this sequence S and subtract, if we take this sum S and subtract off the sequence x times S, so S minus x times S. Okay, so that leaves us basically only with a single term, which is this 1 here, because everything else just cancels. This x here, when you subtract x times S off, that cancels with that x there. When you subtract xs off, that x squared cancels with that x squared, this x cubed cancels with this x cubed, this x to the 4 cancels with this x to the 4, etc. So we get 1 basically. And then if we just factor out the s, we get s times 1 minus x is equal to 1, and then we get s is equal to 1 over 1 minus x. Okay, now, and this basically is our pointwise limit. So now what we just say is, okay, x is general again. X was any element of, could have been any element of the interval 0 to half. This is what it converges to. What we now have is a formula such that if you give me an x in this interval 0 to a half, this is what the pointwise limit is. Therefore, we have a function. So this is our limiting function, basically, which tells us what the pointwise limit of this sequence of functions is as a function of your point in the interval 0 to a half. Okay, right. Now, that is a continuous function on 0 to a half, as we know it must be, because CAB is a complete metric space. We know this converges to something in CAB. We know it has to converge to what it converges to pointwise. This is what it converges to pointwise. So this function must be a continuous function, basically. And if we plot it out, what it looks like, so here is 0, here is the half. If we plot out what it looks like, when we evaluate it at 0, we plug in 0, we get 1 over 1 minus 0, so we get 1. And if you plug in a half, then you get 1 over 1 minus a half. 1 minus a half is a half. 1 over a half is 2. So basically it blows up, well, it doesn't blow up on the interval 0 to a half, because otherwise it wouldn't be continuous, but it gets bigger as you approach a half. Basically it looks something like that, and that's what that sequence of functions converges to. So I hope that was a useful example of how to use these concepts of convergence in that metric space. So a concrete example, basically, of the applications of Cauchy sequences and the application of the knowledge that a metric space is complete.